All right, guys, if you can hear me okay, please let me know. Perfect, perfect. All right. Exactly well. I really applaud your enthusiasm for this class. I know it's pretty late for you guys. Thanks for joining. I know I started a meeting a little early, so maybe we can if you guys have any questions while we wait for others, now's a good time. Anyone have any questions, comments? All right. Oh, okay. All right, guys, while I'm waiting for others, I'm looking at some of the solutions. Hello, guys. Any questions so far from this week's assignment? I have a few changes I want to go over with you guys. Okay. Give me one moment. All right, guys. Why don't we get started here? You can let me share my screen so we can you can see what I'm saying, and we should get going. So now that we have a pretty so what I want to do is start with any questions or comments you guys have. Otherwise, I will start with the reviewing last week's assignments. Let's see. Participant. Okay, good. All right, guys. So this is good. A few changes. If you can see my screen here, right? So one thing I've done is I published this book on GitHub, so it's a little easier to navigate. So if you look at the link on the top, right? If you click on the link is a little different one, but basically if you click on the link, you'll see it's a much easier to navigate format. So what they do is they kind of publish the repository as like a little website, right? So the content is the same. It's just just much easier to navigate, right? So that's pretty much it. And again, the link is already changed in the document, so you can take a look at there. Okay. And although the other links will still work because the underlying repository is still the same. It just GitHub actually render them as a like a book or a website. I thought this is pretty cool. So, a little easier to navigate. Okay, right. So that's one. The other one is I have added some books for you guys to read. So here's the recommended books right here. Again, from the same index, right? So I segment them as like a more high level and more hands-on, right? And most of them are free books, right? I will indicate if it's free, right? If it's something that's not free, you'll see it too. But I mean, it's I highly recommend it because these are really good books, right? But you can start with free books, There are tons of free books that you can start with. Okay, so take a look at that too. Again, like I said, you don't have to read them all. This is more for your reference. I will refer individual chapters as you go through. Like for example, right, if you go through, say, linear regression, which you guys have been looking at, so it'll kind of say, right, there we go, right, chapter 3. Read chapter 3 of this book. Right, that's it. So I don't believe in just giving you guys, okay, hey, go read this book, right? Because that's not very productive. Because it'll take you, a couple of weeks just to get through a book, right? That's not what we are about here. So I will give you very specifics to things to read. Okay, so that's how the course is structured, as you guys know. Good, guys. So linear regression is what we started looking at. There were 2 assignments. One, kind of reading a little bit about regressions, right? Just understanding what is regression, what do we use regression for, just so we understand the business case for it, right? And after end of the regression, we need to be able to answer these questions. For example, if I ask you guys this question, let's start with this. When do we use regression? Like, regression algorithms, like when will we use them? Can anyone tell me? You can type in the chat window as well, please, if you like.
You can use regressions to measure correlation between any multiple variables.
True. Yep. So yeah, variables are like, usually like numeric variables, you can measure correlation. Yeah, very good. Very good. Prediction. Yes. So Mesh, very good prediction. So thank you for that. Also, prediction is very good. But what are we predicting? Like, can you guys get a little bit more specific? Like, give me a use case, for example.
Well, the word regression. Regression gives you a hint. It's actually for things that you know that they're coming back to a specific trend. They're tending to actually go back to some kind of an equilibrium line or
right. Right. Yep.
They regress back to that thing. Yep. That's why it's easier to predict than many other things.
Regression. Yep. Yep. And I see a couple of good answers here on the chat window. You guys can see those too. Like the really good, I like the one predicting continuous data. That's very good, right? So what does it mean? Continuous data basically mean usually numeric data, right? Numbers, like for example, thing like temperature. Given today's temperature conditions, can you predict tomorrow's temperature? And what is the temperature? Just a number, right? So if you think of like, the temperature keeps going up or goes down, just a number. Can you predict, say, stock market? Again, just a number, right? So that's why we like to say them as continuous data. That's very good. And I like David's suggestion to supervised continuous, right? So regression is a supervised algorithm, meaning we train it and then we predict, right? And yeah, so things like prices, right? So this is the reason I ask this, right? This is important, guys. We are going to learn a few algorithms. What you need to develop is a skill to say, okay, if somebody comes and tells you, okay, I want you to write a program to basically analyze house prices. You probably should know, okay, yeah, you can say, okay, yeah, this could be a regression problem, right? And then, okay, and once you narrow down the regression, okay, what are the algorithm we can use? Can you guys name some of the regression algorithms? I know you guys have been looking at some of these blogs I've been asking you to read. What are some of the regression algorithms you can use? So once you decide, okay, yes, we are going to use regression, what are some of the algorithms? Some of the regression algorithms?
Linear regression, obviously.
Yep, exactly. Linear is what we're looking at this week, right? Linear is perfect, yep. What else? There are more than linear. What do you guys think?
Exponential.
Right, there's polynomial, there's a regression tree, right? Basically a decision tree or regression tree.
Also clustering.
I'm sorry?
You can cluster information. You can use clustering information in that kind of, trouble,
Right, yeah, in some special cases, yes, we can use clustering as well, right? So for this purpose, let's just stick with predicting continuous variables, right? Meaning like predicting numbers, on a very simple scale, right? Exactly, I see like things like ridge, lasso, regression tree, right? So these are good. Now, so which one do we use? That's what we are going to learn, right? So we are going to start with a very simple regression, which is linear regression, right? That's very easy to start with. But even when doing something like this, you will learn a lot of the machine learning techniques. All right, very good, guys, very good. Now, what is an error or residual? Oh yeah, so XGBoost is a pretty good one. I'll just mention this. It's basically a variation of the tree algorithm, and trees, and we'll see the trees, a little later in this course. They can use both. They can do both regression and classification, right? So when somebody says I'm using XGBoost or random forest, yeah, right, we know what they mean. Meaning, right, they're using a tree algorithm, so think like a tree algorithm, like a binary tree, like you go left, you go right, kind of a thing. Same thing, right? But more specialized. Very good. Yeah, I like that. Good, guys. Okay, what is an error? Can you tell me what an error is, or error or a residual? Go ahead. Yeah. What is an error, guys? That's right. Right? So error is basically the difference between what I was expecting and what is, what is my algorithm predicting? Like, for example, like, let me go back here, right? So here's an example I showed you guys. By the way, did we go through this with you guys? Because I teach a bunch of classes. I kind of forgot which one I covered for you guys. Did we talk about this tipping example, errors and error squared and all that? Did we go through this with you guys?
I don't believe so.
Okay, good. Okay, thank you. Okay, so let me do that right now because that's why I asked you guys. Because, oh, did we? Okay, we did. Okay, so can somebody else confirm? Did we go through the errors and do the slides look kind of familiar to you guys? Did I go through them with you? Errors and like sum of square errors and all that. Yeah.
I don't think so. I think we discussed briefly in one of the classes that we subsequently.
Okay, yeah. So let me zip through this one real quick, right, because it's important to understand, right? So, okay, let me start with this regression, right? So again, look at the algorithm. This is like an algorithm chart, right? Algorithm, I call it algorithm map. So we are using supervised algorithm. Now you guys know what they are, meaning they involve training, right? And we're going to look at regressions subcategory. And then these are some of the algorithms we are going to look at. So we're going to start with linear, right? Because that's the simplest algorithm. And like you guys mentioned, there are a lot of other regression algorithms, right? We'll start with linear. All right. So the example I showed everybody is like, let's have a very simple example. And this is one of your worksheets today, this week, is let's say I'm sitting at a restaurant. I'm recording, how much was the restaurant bill and how much was tipped, right? So this is my data. So like meal number 1, meal number 2, right? Billing amount and the tipping amount. And when I plot this, now you guys know how to do this, right? So bill example on the x-axis, tip is on the y-axis. When I plot this, this is what I see, right? It's a scatter plot. And when I look at this plot, I can say, this looks kind of a linear relationship, right? Because, you can see, you sort of draw a line, and when one goes up, other one goes up too, right? That's pretty good. So can I do linear regression? Right? That's the idea for this. Now, a little basics, linear regression is, if you guys remember your graph, if your graph classes from middle school or high school, a typical graph goes like this, ax plus b, right? So if you look at a graph like, say, y equal x, let's have the very simple one. So that's a 45-degree angle in a nice slope, goes through 0, right? That's y equal x. If I make y equal 2x, what's going to happen is the slope is going to increase, right? So you can see like from here, the slope is going to go up, but still going through 0. And if I say y equal 2x plus 4, so the same slope, right? The same, you can see the slope is exactly the same, but instead of going through 0, now it's going through 4. So in machine learning terms, we call this as slope, right? How steep the line is. And the intercept is where it intersects the y-axis. Pretty straightforward, right? So just a little refresher on graph theory. So if you look at my graph y equal to x plus b, ax plus b, a is the slope, right? B is the vertical intercept. And when you do linear regression with single variables, right, our line will look like this, right? Because basically, what my data is, this is my x data. Given x data, I'm trying to predict y. right? So, right. So yeah, I see some of you commenting. Yes, you teach algebra at school. So yeah, exactly, right? So a little refresher. I'm sure we all did this, but it's always going to do a little refresher, right? So now we understand the graph theory. So now this section, I said y equal ax plus b, but more commonly you will see this equation beta 0 plus beta 1x, because the thing is, right, this way you can keep adding more coefficients, right? You can say b1 x1, b2 x2, so on and so forth. So it's a little bit more flexible. Either way is fine. You'll see both kind of equations when you're reading books or blogs. So x is sometimes called independent variable because that's what the input is, right? Also called feature attribute. The response y is called, right, y variable, target, outcome, meaning that's the result. That's what we are trying to calculate. Again, this guy is b, beta 0. These are called intercept, right? What is the intercept? Where the line is crossing the y-axis, right? And the other one is called slope, right, or weights, right? Anyway, so this slide just going to give you various vocabularies when you look at regressions, right? That's it. Okay, so we determine our billing and tipping example linear regression, right? Looking at the graph is very simple because there's only two variables, x and y. Right? So remember, what's my equation? Right, this is my generic equation. So when I customize this for billing and tipping, what do? I say tip amount, because that's my y, right? That's what I'm trying to calculate, is equal to a times, we don't know what the a is just yet, bill amount plus b. This is my equation. All right, a times b plus b. All right. So now my goal is find a and b. Like if I find a and b, this formula will be complete. And then you can tell me any amount of bill, I can plug into the formula and I can calculate what the tip's going to be. Right? That's the idea. Right? So how do you calculate a and b? So I actually did the calculation quickly, and to me, a was 0.24, b is minus 1.2. And I'll show you guys how I did the calculation. So my formula becomes like this, right? Tip equals a is 0.242, right? Times bill amount. And b is minus 1.2. B can be negative, right? Meaning my axis can intercept at the bottom, right? So I have below 0. So this is my formula. So again, we will see how I came to this formula, but just go with me for now. Now what I did was, remember this is my formula. What I did was I created another Excel spreadsheet. This is my input data. My input data is bill and tip, right? This is the observed event, meaning this is the actual bill, this is the actual tip. But I also have a formula. When I plug it in into, like, for the bill amount into my formula is going to predict a tip amount. So I do that too, right? That's my next column. So what I'm doing is when I plug in the bill amount, I'm calculating the tip, and this is my estimated tip, right? So kind of, because like this tip is what estimated here. Yeah. Now if you compare these two, compare these two columns, actual tip versus estimated tip. What do you guys see? If you look at the numbers, they are not equal. You can see, right? It's like, some of them are pretty close. Here's 13, 13, 8, 8. These are pretty close. But, this is kind of, right? I have 12, here says 8, 7, 5. So the numbers are not exactly equal. But some of them are close. Some of them are a little far apart, right? So my goal here is I want to calculate the A and B, meaning these numbers, remember? So I can get close to the actual data as possible. Does that make sense, guys, right? That's a game, right? So because I already given you some data, say, hey, this is my bill amount, this is the actual tip amount. Come up with a formula. So when you predict the bill amount, tip amount, you pretty much get as close to the actual data. If you get the exact actual data, that'll be great. That means my model is perfect. But in the real world, we don't get that. But we strive to get as close to it as possible. Okay. Now, so if you look at this data, right? And this is where we sort of look at error function or regressions, right? Right. So let me start with this very simple error function, right? Same billing and tipping example, right? In this case, I'm recording tips, and I want to come up with an algorithm that actually predicts the tips. I took an easy way out. I say, I have a very simple model. The model always says tip is $10, right? Doesn't matter what the bill amount is. I always predict $10, right? So you can see, right? And here's the actual observed tips, right? So $12, $7, $13. But remember, my algorithm, what am I predicting? I always predict 10. right? Very simple algorithm. Now, if you look at the numbers, they don't match, right? So that's a delta. Like if you're a software engineer, you know it's a delta or error. Error meaning how much I deviate from the actual value. So very simple formula. Error formula is actual value minus predicted. So what is actual? 12, right? Minus predicted 10. Right? That's a formula. So my error is +2. Here my actual is 7. Right? 7. Predicted is always 10. Right? Minus 10. My error is -3. So as you can see, right? Sometimes I'm positive. Sometimes I'm negative. Right? But the beauty is when I add these all up, my total errors become 0. So what's happening is sometimes I can predict higher, sometimes I predict lower, right? But at the end of the day, I predicted correctly. So at the end of the day, if you sort of add up all my predictions and the actual tip, they add up to the same amount. That may seem like a pretty good thing. Like, yeah, at the end of the day, we reconcile. However, that's not a great way to do machine learning algorithm, because what can happen is, right? So see here, right? I can make a big mistake on the plus side and the big mistake on the negative side, and they will cancel each other out. So it's kind of like, it's not predictable, right? For example, for some cases, I can predict, really large tips, or, in the other cases, I can predict, really low tips. Just because they cancel each other out is not a good justification. So what we need is we want an error metric that doesn't go to 0, right? That's the idea. So how do we do this? Very simple. What we do is we square the error, right? This table is just as before, right? The first 3 columns. I'm going to get the 4th column. All I'm doing is I sort of square the error. So 2 becomes 4, minus 3 becomes 9. And when you square the error, what happens? The plus and negative signs disappears, right? So now I've squared errors, and when I add them up, they don't go to 0. Why? Because there's no positive and negative cancel each other out, because everything is plus number, right? And this is what I was asking. I'll ask you guys. It is like, look at this column, right? So this column, there's no canceling. And if you add them up, it doesn't go to 0. But can this total be 0 in any case? I don't know if you talked about this, but if you have, right? Can you guys tell me, can this sum ever be 0? What do you guys think? Yes, no, maybe. The squared errors, can it ever be 0? Right. So the only way this can be 0 is when, right? If everything is 0. Think about this, right? Because remember, there's no canceling, right? Everything is a positive number. So the only way total can be 0 is when all the errors are 0. Exactly. What does all the errors 0 mean? Meaning my prediction exactly matches the input. Perfect model, right? So if my model can exactly predict what the actual expected tip is, then my delta is 0, and when you square the 0, you get 0, right? Everything becomes 0 here, right? Everything is 0, square them as 0, and then you add them up 0. So perfect model, 100% accurate model, I get 0. Very unlikely, right? We hardly ever get this, but there's a tiny probability it can happen, right? So yeah, so this can be 0, meaning if you manage to develop a perfect model, yes, sum of square errors is 0. Okay, now this mechanism, right? You know how we calculate the error. The error is actually actual minus predicted, and then we square the error, and then we sum it up, right? This metric is called sum of squared errors, right? It's called SSE, sum of squared errors, right? Just very simple. That's right. Yep. So it's like winning a lottery, right? You hit the numbers perfectly, hit all the numbers perfectly, exactly, right? So the reason I'm spending time on this one, this is a very important metric, sum of squared errors, because when I'm designing an algorithm, I want to minimize the error, right? Right. So when you're for example, when you're writing an exam, you want to minimize your errors, right? When you're driving, you want to minimize the time spent, right? We always minimize for something. We always try to, the other word we say is we always try to optimize for something, right? So I want to optimize for the error, right? Meaning I want to take the error as low as possible. So one of the popular error we optimize for is sum of squared errors, SSE, right? right? So here's the formula, right? Again, you must see the formula. It's not, I mean, it may seem a little intimidating at first, but it's very simple. The way you read this is like this. So Y is actual. Y hat with a little hat here, right? That's predicted, right? So if you look at this is actual, this is predicted, and we calculate the delta, and then we square them up. Why? Because square them actually, mask the plus and negative numbers, right? And we add the sigma is basically adding them all up. That's it, right? So if you can start reading the formula, it's not that mysterious, but you'll see this formula quite a bit of time, right? Sum of squared errors, very important metric, right? So, and in practice, we use a slightly variation one. We take the sum of squared error, right? Same thing, same formula. You can sort of see the formula, right? Formula is exactly the same, right? And then what we do is we divide the error by number of samples. We sort of take like an average, right? That's why it's called mean, right? So mean sum of squared errors, also known as MSE, right? So when you do regression algorithms, a lot of the time you will actually calculate the MSE, mean squared error, because when you're adding them up, I want to calculate kind of the average error, right? Basically, that's what I mean. So if you look at the table, I'm not going to go through the table, but you guys already know the table. If you look at the numbers, right? Actual error, squared errors, right? We add them all up, 76, right? Total. And I have 6 samples divided by 6. My MSE is 12.6, right? So this is one of the common error metrics we use. Okay. And because you'll see this when you do a regression, right? And there's another metric you can use. Remember, the reason we square the error is because we want to disappear the negative signs. Right? You could say, hey, wait a second, why am I squaring? Why don't you just simply drop the sign, right? And then just take the number values. You could, right? There's another metric. It's called mean absolute error, meaning we only take the absolute value, right? For example, you take the error, right? Here's my +2, -3, right? This is a regular error. I simply drop the signs and I take the absolute value. So +2 becomes 2. -3 also becomes 3. So signs disappear, right? And again, how to calculate the same thing, right? So if you see this little bar, that means the absolute value, right? We are adding up all the absolute values, right? And also dividing by the average, right? To get the average mean, right? That's why it's called mean. So anytime we use mean, that means we are dividing by number of entries, this. So I can put them side by side so you can sort of see here, right? And one thing you will see is the error squared is always a higher number, because we are squaring the error, right? And sometimes, again, we're not going to go too much into this because there's a lot of stats behind this. Sometimes you want to actually use the squared error as your metric, because what it does is it actually amplifies the, right? When you make large errors, your errors are really amplified. See, so I made an error -5, let's say, right? In the absolute error, my error is just 5 because we're just taking the absolute value. But when I square the error, my delta is 25. Why? It's amplifies. So kind of, right? It really sort of amplifies the algorithm, meaning all the outliers, now you guys know what outliers are amplified here. And that sometimes helps the algorithm to converge faster. So if you ask me, which one should I use? Should I use MAE or MSE, right? There are 2 camps to this, right? I always say, right, there's no hard rule. So start with one. And a lot of the time you will see people starting with MSE, right? Because that's sort of the, seem to work in most real life scenarios. Try with MSE, right? If it doesn't work, right? Also try with MAE, right? And then see which one gives you a better algorithm, right? That's it, right? There's no like a hard and fast rules, but now you can say no, both algorithms, okay? That's it. And in most algorithm libraries will let you use these, you can plug in whatever the error metric you're going to use, okay? So that's it. So okay, let me stop here for a second. Does it make sense, guys? Right, MAE, MSE, right? Again, like I said, there are some edge cases when one will make the difference than the other, right? So again, look at kind of, if you read some, I think one of the example I gave you was, right, understanding a residual, right? So for example, right, there's one kind of goes through MAE and MSE, right? Which one's better? So read this again. Like I said, is a kind of, then we are getting into the weeds. For the most part, you don't have to worry about it. You can just choose one, and right, and then when you try the algorithms, you can very easily substitute one for the other and try and which one, right? So again, right. So again, like I said, now we know the basics. once you know the basics, then you can sort of deep dive into more advanced, like which one should I use and all that, right? And then there are some, you'll get into some of the stats theory and all that stuff, but if you're looking for that, look at the reading material, right? All right, so now back to this, right? So kind of, right, sorry, here, right, when I draw my data, right, my linear regression, right, these are my data points. If my line exactly goes through all the data points, it's perfect model, right? But most of the time, my line is not going to go through all data points. It's going to be like this. So these little deltas, like little distances, are what we call residual, meaning, right, what the actual value is and what the difference between my model. Again, we kind of want to minimize this, right? I kind of want to draw a line, like for example, I don't want to draw a line like this, right? For example, right? That's not a great line, right? Because why? My deltas are, high. So maybe, lines kind of go through this. That's the idea. Does that make sense, guys? Right? So hopefully, I think that makes sense. All right. So, right. So the question was, yeah. So the reading materials, guys, right? The way it organized is, go back to the main book is basically, right? I also gave you some regression, fundamental regression. Again, this just, there's no exercises, just some, excuse me, just some basic reading, right? Just so you understand some of the regression models. And also you can sort of, understand different errors, right? So now we understand different errors, right? What are some of square errors? What is MSE, MAE, right? RMSE, root mean square errors, basically, right? It's basically we take this guy and take the square root. Because why? Why are we taking square root? Because remember, this error is actually squared. That's why it's called squared error, right? To bring it back to the normal scale, we take the square root again, right? That's it, right? So anyway, you should be comfortable kind of, understanding these terms. So when somebody says, oh, my RMS is this, what are they talking about? Basically an error, right? That's it. So, good. Any other questions, guys? So that's one, and then also linear regression, right? And also, guys, one thing I want to say is just to kind of, right, I'm kind of refactoring. Sometime when I'm going to keep, updating this, I'll say, oh, maybe, this will go in a different place or refactor. So sometimes the links might change, but I always recommend you can stick to the top level README. That'll always have the right link. Okay, for some example, you have a link and it's not working. Just look at the top level book, and that'll always have the link. Right. So just because it's just kind of a growing pains, and sort of refactoring and updating and all that. So okay, just a word of warning. All right, guys, and then we're going to read regressions, right? So regression, this is a pretty good video series. I gave you a bunch of videos, and it's a pretty detailed, right? And I'm sure you guys have probably gone through this. Brandon Folds, he has a lot of videos on YouTube. I really like his video series, right? It's a little, it takes, each video is about 20 minutes, but it's well worth the watch because, it really helps you understand the concepts, right? So I hope you guys had a chance to kind of go through them. So I kind of, did the basically video series here, just to, I think that is pretty good. Yeah. So, so I know some of you preferred video, some of you preferred reading materials, so I'll kind of mix in both, right? But this one is a little bit more video heavy because, once you watch this video, you will know pretty well, right? Excuse me. Okay. Right on. What else here? So when you do regressions, let me do one more thing real quick, and then we'll look at the exercises. Okay, so now we understand errors, residuals, all the good stuff. Okay, back to our billing and tipping example. So remember, right, this is the actual tip. This is my estimated tip, right? They're kind of close, not exactly equal. So my goal is, remember the formula? I have to figure out this formula, value for A and B, right? So my estimation gets close to the real value as possible, right? How, right? How do you figure out A and B, right? I can just randomly plug in numbers, right? And I can say, oh, okay, let's have the A equal 10, B equal 20, right? I'm just making this up, right? And then plug this in and then say, oops, okay. And then I sort of plug in the formula, calculate the differences, and I say, okay, what's my error? Oops, error is too high. Okay, now I'm going to adjust from, I'm going to increase, A from 10 to 11, and B, I'm going to decrease from, 20 to 15, right? And plug it in, calculate the differences, and add up the error, and then say, okay, now the error is kind of going down, so I'm going to go in the right direction, right? So that's the game. We have to guess the value of A and B. So we don't want to do randomly, right? Because that'll be an infinite number of combination. How do you do this smartly? And this is where a nice algorithm called gradient descent comes in. So let me show you the gradient descent algorithm. Very simple algorithm, right? Sorry, very efficient algorithm, but the concepts are very simple. So let's say this is my variable x, and this is the error. So when I use my variable, my resulting error is this. So it's like this curve like this. And if I ask you guys to say, okay, find me the x that gives me the lowest possible error, you say sure, right? Look at the curve, it's right here. This is the value for x that gives me the lowest error. Remember, error is not 0, but lowest, right? So when I use this x value, you will say this is when that produces the lowest error. That's great, right? So very easy, right? We look at the graph and we say, yeah, this is the lowest value. Now here's the complication, right? What if I don't show you the graph? And then I say, okay, find an x that's going to give me a lowest possible error. Where do we start here, right? So, and this is exactly what happened in machine learning. For example, right? I just gave you guys, this formula and said, okay, find out the value for a and b, right? That's going to minimize my error. Like that, right? So you can sort of see the connection, right? So you have to find out two variables, but let's start with one. Let's say there's only one variable, x, right? I want to find the lowest possible x, but I don't know what the graph looks like. Okay, so what we do, we have to start someplace, right? So what we do is we start randomly. So I just choose some random value, right? So let's say it's my first x1 is a random value. I calculate the error, right? I just plug into the formula, I calculate the error. Another thing I can also calculate is I can calculate the error slope of the graph, right? When you look at remember when you look at the graph, this is the slope of the graph, right? So the slope of the graph, I can calculate that too, right? Using a mathematical formula. So what I'm doing is when I random x, right? Just pick the x randomly, calculate the error, that's the dot, and the slope. Now, question for you guys. So I'm here. My error function is kind of sloping this way. Now remember, my goal is to minimize the error. So if I'm going to go to the next, pick the next x, right? Should I go this way, or should I go this way? What do you guys think? Left or right? Remember, my function is kind of sloping this way.
Right.
I should go right, exactly, right? Because I can say, okay, the function is going to slope in this way, so my chance of finding a lower value, if I kind of go this way. Exactly, right? So that's what exactly what we do. My next value is another random value, right? Again, I just imagine I'm sort of taking a jump, right? So I went from x1 to x2, another random value, right? Same thing. I calculate the error and I calculate the slope. All right, so looking at the slope, what do you guys think? Right, my error function is kind of sloping this way, and I want to find the lowest possible error. So which way should I go? This way or this way? Again, to the right, right? Because my function is kind of still sloping this way, right? So I'm gonna go to this way. So I can keep jumping. That's my next value, x3, right? I'm gonna keep going, and this is basically what gradient descent algorithm does. So right here's my starting point, right? I take a jump, I measure the slope, I take another jump, right? So I keep jumping, right, until I find the lowest point. That's it, nothing magical, right? But we sort of go systematically, right? The way we go systematically is we measure the slope of the error function, and we sort of jump in the direction. And this is exactly what the gradient descent algorithm does. It takes multiple jumps to find the local, the lowest possible error. A few things you will notice. Each jump, right, basically, it takes a calculation. That means that you're sort of taking a new value for x like this, right? And you're plugging into the formula, calculating the error, right? So each jump is not free. It takes compute resources. So you kind of want to find the lowest point as quick as possible. Right? You don't want to, like for example, if an algorithm finds the lowest point in say 10 steps, and another one finds in 20 steps, you prefer the algorithm that does it in 10, right? Because that means less computation. So one thing we want to do is we want to kind of find the lowest point as quickly as possible. Another thing you will notice is initially it takes big jumps, right? And as it approaches the bottom, the jump space kind of narrows. It takes the smaller and smaller jumps, right? Because why? I don't want to overshoot and miss the bottom. So they'll kind of automatically kind of adjust the, right, error kind of slowly, right? So I take smaller jumps because I don't want to miss the bottom. That's it, all right? So that's going to make sense, guys, right? Gradient descent algorithm, right? Now you'll see there's another problem here, right? And that's what keeping you ask me, right? For example, what if I sort of land here, right? It's like, and if now you measure the error here, I mean the error slope here, that is, that is flat. So you might think I have reached the bottom. Kind of the idea is like, imagine I'm rolling a marble, right? So the idea is the marble kind of comes down and then kind of settles at the bottom. But what if the marble kind of settles here? Because the marble thinks, okay, it sort of bounces back a few times and says, okay, yeah, I found the bottom, right? But it's not. So that's why this is called local minimum. The actual one is called global minimum, right? So imagine my marble kind of settled down here. How do you do that? How do you deal with the scenario, right? And that can happen because I mean randomness, right? We can actually, we can get stuck. So again, random to our rescue. So what we do is we do multiple random runs. So let's say I do one run here, right? So this is run one, started here, took a couple of jumps, and then sort of stuck at local minimum. And it says, yeah, this is the bottom for me. Okay. So we do another run. So let's say in this run, it maybe starts here. Okay, it says, okay, again, randomly, right? Just gonna keeps jumping, right? Keeps finding and says, oh, this is, and I found another bottom, which is here. We do another run. Let's say, this run starts here, then sort of jumps, kind of jumping this way and then finds this one. So then we say, okay, aha. So this is the lowest point. I mean, if you're unlucky, maybe, there's even a lowest point, maybe, somewhere here, right? Maybe we missed that, right? But the idea is when you do multiple random runs, you tend to find the lowest point, right? Even if some runs get stuck at local minimum, right? When you start, since you're starting randomly, you can sort of, you can rely on the fact, not 100%, right? With a high probability, you can land on the bottom. Does that make sense, guys? Right? So how do we deal with the global minimum, right? So yeah, so mathematically solving this is, I mean, people have tried to do this mathematically. It's almost one of the unsolvable things, right? Because unless you know the whole graph, you don't know the other minimums, right? So the practical approach is basically what we say is, okay, let's do multiple random runs. So this way, we increase our chance of finding the lowest possible place. That's it. Right? So this whole thing, right, is how gradient descent works, right? Again, very simple, right? We're gonna start a random point, keep jumping, right, until we find the lowest point. Now, this is, I'm changing one variable, x, right? Only one variable, x. But remember, in my formula, I had to figure out two variables. So now my error function, right? When I have one variable, my error function is just a simple line. Because I'm only changing one axis. If I'm changing two variables, remember a and b, now it's like a slope, right? They're gonna make sense. So imagine you had a sort of a, like a ski slope, right? And only thing you can feel, you're standing at the top, only thing you can feel is that the slope at, at your feet. You cannot see anything else, right? So I'm asking you to come to the bottom. So just by using the feel, you're sort of taking multiple jumps, right? And eventually you find the bottom, right? So why? Because I have two variables, a and b, and you can see kind of like, imagine you're just, like a skier, right? You're taking multiple jumps, eventually come into the bottom, right? Now, what if I had a third variable, a, b, c? Let's say I have three variables. Can you guys tell me what the shape will look like? Like, with two variables, it is like a, right? It's like a surface. But three variables, can you guys envision what the three variables would look like? What do you guys think? Can you guys visualize?
I want to say a plane, maybe more curvature.
Yep. So plane is actually a hyperplane, right? So now you're kind of thinking, visualizing in 4 dimensions, right? Because right, ABC, you're kind of you're changing, right? ABC as well. So like 4 dimensions, right? So I cannot visualize it. So I can go up to 3 dimensions to visualize. More than that, I cannot visualize. But no big deal, because math doesn't really care how many dimensions we have, right? It could be 2 dimensions, 20 dimensions, the math is the same. It's it's more complicated because you have to do more computations, but the math is just the same, right? So that's why we use design algorithm. Doesn't matter how many dimensions we are, how many variables we have to adjust, it'll find the solution. Right. All right, guys. So this is essentially gradient descent algorithm, right? I mean, there's a lot of math behind this, as you can imagine, right? People have spent years, getting PhDs in finding out the best possible gradient descent algorithm. But the concepts are easy to understand. Like we get it. We're like, oh yeah, I see what's going on, right? I just started some random position, kind of, just by using the slope. So by the way, I see some question in the chat window. How do you measure the slope? So the slope is basically your derivative, right? You kind of look at the graph theory. Let's say if somebody says y equal x squared, what's the derivative, guys? What is derivative y? Anyone?
1/2.
Yeah,
2x,
right.
something like that.
Right, exactly. Remember, so x squared will be sort of like this, right? It'll be like what is x squared? Yeah, it'll be like this, right? So derivative will be, the slope, right? So 2, all right, or something like that. I forgot. It's been so long, guys. I forgot, right? Basically, we take the derivative, right? 2 or 2.5 or something, right? 2x. I'm sorry, yeah, 2x, right? So remember that. So how do you? That's how I calculate the slope. So you guys ask me, how do I do the slope? Slope is simple derivative. That's it, right? So. And that's why we.
But we don't know the graph. How is the graph at the beginning when you were explaining?
Oh yeah. So okay, yeah. So you're right. I don't know the graph just. However, I know the basic equation, right? I know the basic equation is like this, right? So that's what I start with. So I kind of know that. So I have some basic idea of the equation. Now I don't know what A and B are for sure, right? But I do know the basic equation. That's why.
So
because we assume, right? Remember, and that's a big assumption. We assumed, this is a linear relationship. And if I do linear relationship, this is my graph. You can say, okay.
Substitute the A and B with some assumption.
That's right. And exactly, right? So what if you say, oh, my equation is something like this? You say my equation is like, ax cubed, just like this, right? I'm just making this up. Bx squared, cx plus d, right? So this is a much more complex equation, right? So I have a cube, squared, and a variable, and a plus a variable. So now I have a, b, c, d to figure out, right? So, and because we assume that, because looking at the equation, we are assuming, yes, we are solving a linear equation, right? This is the fundamental equation. So that's where I get the derivative from. Exactly, right? So, so this is a polynomial equation, right? This is a polynomial equation. And if you think, okay, this is a polynomial regression, then, then this is the equation. So yeah, you need to sort of start with some notion of the equation. So you can, you can actually tweak this variable, right? Yeah.
And how many random runs are necessary?
Good question. The latest ones, the data is pretty simple. They will basically easily converge anywhere from 10 to 100 runs, right? So like if your data is pretty simple, just a handful of runs is all it needs for the function to find the lowest point. If your data is complex, then it may take maybe 50, 100 runs, right? Sometimes it may not even converge, right? Sometimes it may not be able to find a solution. So in this case, we say the equation has failed, right? But most in real world, like just 10 to 100 is kind of what I've seen, right? So.
And how we can understand this is the local or the global, and then figure out if we should continue, we should not, and
right. Good question. So the way you're kind of right. Remember, you're doing multiple random runs here, right? So you're kind of with a reasonably certain degree, you can trust you find the lowest point. It may be, right? You can argue there's a tiny possibility, you kind of, all the algorithm gets stuck in this point. Technically possible, right? But practically, since we do random and we start random at multiple points, right? We can be reasonably, degree, we say, yes, we find the lowest point. Yeah, that's why. So, and remember, when you're done your grade, it's an algorithm, it will do this for you automatically, right? They will do multiple random starts, and they will look at the derivatives, and they will do all this work for you, right? And that's why using these guys is very straightforward. Now we understand the sort of the basic thing, what's going on. when you use these guys, right, they will kind of do all this work for you, right? And that's why machine learning has become more approachable now, because I remember when I was learning machine learning, we had to really write all these things on our own. Right? We had to write our own gradient algorithm in C, right? And then do regressions. And I mean, these are these may seem trivial, but these are not easy to implement, right? Because the algorithm, they're like, for example, how do how do you make sure you take smaller and smaller jumps? You know what I mean? There are a lot of math goes behind this, even like something seemingly simple. So implementing this from scratch, we don't do that anymore. I mean, I used to, right? Because I'm old enough here. I used to implement this in C code, and I can tell you, you can spend a couple of days just writing gradient algorithm. Now the beauty of machine learning now is all of these are now the high quality libraries are open source, and they do this for you behind the scenes. So we can just use them, right? We don't have to start from scratch and kind of write all this. It's all done for us. So we are going to use those, but the reason I'm sort of spending some time explaining this to you guys is we want to understand what we are using. Right? So we're not just blindly just calling a function. We kind of know, okay, what's happening underneath, right? So yeah, so I for one, I'm glad all these libraries are open source, because I remember how painful it was to kind of do all of this from scratch. So, and this is another reason machine learning has become very approachable now, right? Because all these high quality libraries become open source. Good, guys. Okay, let me look at the chat window real quick. Right. Yep. So derivatives again. If you really want to understand the algorithm, trust me, there are hundreds of white papers. Like I said, people have spent years getting PhDs in figuring out what's the best, how to best do gradient algorithms, right? But the basic concept we understand, right? That's all we need for our class. All right, guys. Any other questions on this one? This algorithm works, right? So, right, you can sort of see here how we went from single dimension, one variable, simple line, right, to 2 dimensions, A and B. So now it's like a slope. Beyond that, we cannot visualize, but doesn't matter, right? That's what the design algorithms. And at the end of the day, guys, these are basically comes to matrix calculations, right? And computers are really good at that. Okay. And here's a couple of animations, right? You can sort of see here, right? So here's like a little, my slope. So these are like control lines, remember? My bottom's at the bottom, here in the middle. So you can sort of see the algorithm kind of coming down, right? And as this approach, just takes smaller steps until it finds the bottom. You can see, right? Big steps initially, smaller steps. And here's another one, right? So here's a kind of mapping this to like a linear regression. So imagine this is my error curve, right? Again, the bottom is right here. You can see I'm sort of starting all the way to the top and then kind of taking bigger jumps, and you can see the jumps kind of get smaller and smaller, find the bottom. Look at this line, right? It's kind of going kind of rapidly, but you have to see it, right? So I'm initially drawing a line like this, right? So that's not a good line, right? That's my initial line, right? And as it keeps taking the jump, see how my line kind of shaping up to map to kind of to align with the data points, right? So because that means I found the bottom. Pretty cool, right? So this is one of the really good animations I liked. You can see initially my error, look at the error value. The initial error is pretty high, right? Because I'm just drawing like random line. And as I'm doing my gradient descent algorithm, as I'm trying to going down the slope, keep jumping, my line gets more and more refined. And once I reach the bottom, my line is perfect. I mean, perfect as in it's not it's not 100%, but as perfect as we can get. Pretty good, right? Yeah. So that's how you sort of map. I mean, again, I kind of want you guys to think like okay, this is the theory. Gradient descent. Okay, we get it, right? We find the lowest point. We make multiple jumps. How does it map do regression? Like here, right? It basically shapes the line into a format that aligns with the data points. Yeah. Right. So don't look at this for too long. I mean, these are like GIF images, and I wish there was a way to kind of slow down their thing, but yeah, it's what it is. But anyway, I mean, somebody has done the hard work, right? I got it from somebody from the internet, but yeah, I think this is a really good animation. Good, guys. All right. So takeaway, right? So we're going to go back. Like I said, there's a range of gradient algorithms. The one we use is basically right now the popular one is called stochastic descent algorithm. It's commonly known as SGD, right? So if somebody tells you we are using SGD, this is what they mean. By the way, this is the same algorithm we will use in deep learning as well, right? Even in deep learning, people say, oh, we are using SGD algorithm. This is what it is, right? So why do we prefer SGD? Just to kind of give you a little understanding. First of all, right, is very effective even for large data. So if your data is pretty large, still it can't find the minimum, right? It's just, just like I said, usually like, a few tens of passes to converge. The algorithm is pretty good, right? And also, it's very good about not getting stuck in local minima. Remember local minima, right? Imagine kind of rolling a marble, kind of getting stuck here, right? So the SGD algorithm is very good at avoiding local minimas, right? Anyway, right? So you can look at all the. If you're really curious about the math, do a search for SGD, and you'll find the white paper, and you see all the math details if you really want, right? So, all right. So, all right, guys. End of gradient descent. Any questions? So this is the important concept. I want to make sure you guys understand this, because this will come up in pretty much all the algorithm we use, right? In all the algorithm we use, when we try to find these optimal value, when I'm trying to find my equation, remember, let me come back to this one, right? Sorry, equation is, go back. When I'm trying to find this equation, these are called coefficients, by the way, right? When I'm trying to find this, right, again, we don't want to just randomly plug in values and hoping the error is going to go down. We want a systematic way of doing this. How do we do this? Right, descent, right? So gradient descent is where we started at some random point, like you guys can see, right? You can still see the animation here, right? All right, start at a random point. This is the error. Take jumps to minimize the error. How does it kind of map to right, like this, right? So I'm starting a random point. My line is kind of right somewhere here, and as I'm going to keep going down the slope, right, my line gets more and more refined. All right. So where do we use gradient descent? Pretty much all the algorithms use gradient descent algorithm, right? Because remember, this is what machine learning is, right? Machine learning is like you start some random value, and you are going to optimize your equation, right? How do you do that? Pretty much all the algorithm underneath use some form of gradient descent algorithm, right? Whether it's linear regression or classification, right? Right? A lot of them will use this. Okay. So hopefully this made sense. And also, I mean, this concept, not only in machine learning, it also comes in deep learning. And so a lot of the deep learning algorithms use gradient descent algorithm to during training. Right? So very important concept. So again, I hope I gave you guys like a little high level, right? Again, I know we didn't go into the math of anything, but we don't need to. Understanding the concept, we get it. Like I'm look at this, I'm saying, sure, I see how this will work, right? Get the slope, find the lowest point, do it as quickly as possible. Don't get stuck in the little gullies, right? Yeah, we get it. All right, guys. Good. Any other questions on the gradient descent algorithm? So I hope it makes sense, right? Again, most common one right now, that's SGD is what we use, and there are a lot of other variations. I mean, there are at least at least a dozen or so variations, right? So, like I said, people have spent time getting PhDs in this, right? So that means it's complicated enough. There's a lot of research went into this. Okay, back to our equation, right? So you guys know all this by now. Okay, so we, now our metric, I'm going to find the equation. I'm going to optimize for errors, right? The error I'm optimizing for is sum of squared errors, right? Because that avoids, positive negative cancellation, right? And these are the formulas, right? These are, it's all familiar to you guys. That's right. Math is useful. Yeah, may not be obvious all the time, but yeah, sometimes it is useful, right? So here's another one I'm going to introduce you to guys, and this is something you guys did on the very early days called Pearson correlation. Remember correlation coefficient, right? Meaning I give you guys two variables, and then I say how correlated they are, right? Again, remember correlation between -1 and +1. Right, that was normalized. So +1 meaning they are perfectly correlated, meaning when one goes up by 10, the other one also goes up by 10. Right, that's +1. -1 meaning it's negatively correlated, meaning like one goes up by 10, other one goes down by 10. Right, 0 meaning no correlation. So when I plug in this formula, when I plug into the building and tipping data, my correlation coefficient on R comes out to be 0.95 or 95%. Right? Right? 95%. Right? So what it means is building and tipping are very highly correlated, meaning when the building goes up, tipping goes up. Sure, we know that, right? When you have a large check, you leave a large tip, right? But now, I can confirm this with the formula. So when I plug in my data, my formula says, yes, 0.95 meaning it's kind of right there, right? It's like, one is a plus one is a maximum, so 0.95 meaning it's kind of right there. So, almost perfect correlation. Pretty good, right? So again, yeah, somebody mentioned correlation, not causation. Yes. Do a search for that one. You'll find some really interesting anecdotes. Correlation is not causation, right? But correlation tells you if how two variables behave. All right, so that's one metric, right? R, and R is looking pretty good now, right? I can say these two variables are highly correlated, so that's very good, right? There's another one called R squared, right? And this is called coefficient of determination. So R squared 1 indicates a perfect fit. And when I plug my data and I calculate the R squared for my equation, if I get 1, perfect, 100%, right? So let's do the R squared for us. Again, I'll show you guys this formulas for all of you guys, when I do the labs. R squared, when I plug in the R squared, I get 90%. And again, these are like 1 is the highest, right? So I'm 90%. That's very good, right? So this is called coefficient of determination. What it tells you on a very high level is how well my model can explain the data. Because remember, we are creating a model that actually is going to explain the data, right? Or predict the data, right? So in this case, my model can explain 90% of the behavior. And if you ask me why 90%, why not 100%? Remember, in real world, we don't get 100% accuracy, right? Because there's always some noise on the data, there's some errors, right? So getting 100%, especially in regression data, is very, very, very unlikely. But 90% I'll take it. Right? That's pretty good. So my model, my simple linear regression model, can explain 90% of the behavior in the data. Right? All right. So, all right, guys. So I will let me sort of skip through some of these. All right, so now we are getting into our labs. So let me look at the labs you guys have done. Before we go to the lab, guys, any questions sort of the basic theory, sort of the linear regressions, gradient descent, kind of the, right? These are some of the important concepts we want to understand. Errors, right? Yeah. Any questions? All right. So let's review. So the lab solutions, if you look at this, I uploaded the lab solutions here for you guys, right? I opened up the submission files. So I'm happy to see like a lot of people are submitting solutions. That's very good, right? I have also uploaded my solutions as well, so you can take a look at this. So these are two, my two algorithms, right? One for tips and one for house prices. I want to actually highlight Ahmed Jalal's solution. I thought this was pretty good. So, right. So thank you, Ahmed. I don't know if you're here today, but thank you so much for submitting solution. All right. Oh, there you go. Cool. Thank you. Yeah. So I can ask you guys to say, okay, look, let's do linear regression, but let's start with like a very simple data, right? If you guys look at this, right? Because you're going to start with real world data, but I said, no, let's start with some synthetic data. How do we generate synthetic data? This is the make regression function in scikit, right? Remember, this is what you guys did yesterday, not yesterday, last week, right? Kind of playing around with these guys. So by the way, right, when you guys open up the right, like for example, when you guys open up my notebook, for example, right, say open with Colab, right, always make a copy, because otherwise you will not be able to save. You simply say file, make a copy, right? Because otherwise, your changes are going to be lost, because you only have a read-only view. And then what it'll do, like, you'll like to save in your Google Drive and open this one, right? Oh yeah, no, don't worry. I mean, yeah, there's just thank you for submitting. I'm going to highlight just a few cells, right? So don't worry. Again, like I said, don't get nervous if you didn't complete the whole thing, right? All right, guys. So pandas numpy. So here's my scikit, right? Okay, connecting. There we go. All right. So function goes like this: make regression. Okay. I'm saying generate 100 data points, number of samples, and only one feature. All right. And so the way make regression will always give you X and Y. Okay. Now, if you're wondering why X is always capital, Y X, and then Y is small letters, It's a bit of a custom. I will explain this in the next lab, right? But for now, just assume if you say simply X and Y, nobody can fight with you. It's just a custom, right? The reason is X can be multiple values. Like for X can stand for like X1, X2, X3, right? Multiple vectors. That's why it sort of says as capital X, and Y is usually one vector, right? Just Y is usually like just Y, right? Just single dimension, right? There's a Y. But like I said, you can just call it A and B. Nobody would care. It's just a convention, right? So if you're kind of wondering why is X always capital, because X can stand for multiple vectors. That's why, right? But at the end of the day, it's just a variable name, doesn't matter. So make regression gives you two things, X and Y. So we kind of print X and Y. Okay, right? Remember, this is all random value, right? And okay, so I see like an array of numbers, array of another numbers. Okay, it doesn't make a lot of sense. So let's kind of plot them, right? So I can say scatter plot, right? There we go. X here, Y here. So you sort of see that's pretty cool, right? That's that's like a string line. If you can, because here we're adding some noise. So we made the noise to 0. Let's try this. Let's make the noise to be 0 and plot this. You will see the line is much more in line. So noise you're kind of noise, like you're adding a noise a little bit just to make the data a little bit more interesting, right? So let's say I'm adding noise, say 10, just just a number, right? And then if you just do this, you will see much more, right? Right? Number is a little bit more distracting. Anyway, you can play around with this. So this is pretty cool, right? Just in a couple of lines of code, Scikit can generate some regression data for you that we can play around with. Okay, so all right, let's do regression. So we are going to use X and Y here, right? My X and Y is already given by nice numbers by scikit-learn. Very good. So we don't have to worry about data formatting and any of that, right? So here's my linear regression. So again, scikit-learn linear model, import linear regression, right? So we simply say fit X and Y. So this is basically my training, right? I'm saying, okay, this is a linear regression. Here's my data. Go ahead and find the coefficient. When I say coefficient, these guys, right? Go ahead and find my A and B. Remember? Can remember the formula here. Go ahead and find my A and B, right? Using this data. That's it. So it's gonna sort of try this data, gonna come with different A and B's, plug into the data, and try to minimize the error, right? Again, it's gonna use gradient descent at the bottom, right? So as you can see, right? So right here, it's using gradient descent behind the scenes. We don't even see it, right? We just say, oh yeah, I simply say, okay, fit the algorithm to the data. Remember the formula, algorithm plus data gives me a model. And that's what I so so at this point, just an algorithm, right? When I say fit, it trains the model internally on the data. What's the data? X and Y. Does that make sense, guys? Kind of on a high level what we are doing. And this is the exact same steps you will do in all the labs, right? Define algorithm, we simply say, fit X and Y, okay? And once it's done, right? So here's my regression algorithm is done. So okay, let's print out the coefficients. It says, coefficient is 31, intercept is this. And we're wondering what is the coefficient? Is this guy, remember? Because we only have single variable, right? Remember the graph, our graph theory. Come on. Where was that? There we go, right? My coefficient or the slope is number 2, and the intercept is 4. All right, that's it, all right? So coefficient is 1, intercept is this, okay? So now my model is ready. So here I can say, okay, now what, go ahead and predict on some data. And here, I can just, I'm using the same data. That's fine because it's the simple data, right? X, bring the data, and I give you something, give you some data. How does it look? Let me plot. There you go, right? So what's the plot says? The blue points are my original data, which you can see, right? This is my original data. Remember, I added a lot of noise, right? So data is kind of scattered, right? But it's still kind of following a linear pattern here, right? So that's my original data. The red data, right, is basically predictions, meaning what the model is predicting, which is basically the model. And you can see it's kind of going through, it's drawing a line kind of in the middle of the data point, right? So if you look at this, I mean, some of the data points is going through. This is very good, but here, is deviating, right? Here is deviating. So I mean, yeah. So overall, you can see, right, it's going through pretty well across. Through midpoint. That's it, right? So okay. So what's the biggest takeaway, right? So first, we generate data. We create X and Y. In this case, we took a shortcut. We asked Psyche to generate some X and some random data for us, right? That's good. And then we sort of plot the data, kind of see, okay, yeah, this looks linear. And then just 2 lines of code, right? Initialize linear regression algorithm and simply say fit on X and Y. And when you print the coefficients, right? You sort of, we only have one coefficient because there's only one X, and the intercept is where the intercept. That's it. Any question on this one, guys? And we sort of plot this. And by the way, here we can plot this because it's a 2-dimensional data, right? Just X and Y, so we can easily plot. But what if your X is like 10-dimensional? Then the plot's not going to work. We can visualize it. But here, just 2-dimensional data, right? X and Y, so we can easily plot and kind of visualize the data, which is great. Yeah. Good, huh? So, so this is very good, right? So this is a good notebook. So thank you, Ahmed, for doing this, right? So remember when you calculate the error, we talked about the errors, right? Here, yes, we are calculating the error. So it's part of the scikit-learn metrics package. So we are getting the mean absolute error, which is basically, what is mean absolute error? MAE. Sometimes you will see people noticing this mean square error, MSE, right? So what's my MSE? Mean square, again, simply mean square, I simply give Y and predictions. Now this is important, right? I mean, so this is, I'm gonna say calculate the error, expected, predicted, right? So, I mean, it's like, I'm giving you a test, right? I'm saying, okay, so I'm giving you 10 questions and I'm going to give you a score. For all 10 questions, I know what the expected answer is, but I'm comparing my expected answer with the answer you predicted. If you get all 10 right, you get 100%, meaning, your error will be 0, right? Is that going to make sense, guys? So sometimes people get confused here and say, I need to do X and Y. No, you don't do X and Y. Remember, that's not the whole point, right? Because X is the input. So kind of the way you're thinking is like this, right? So we say X is input, Y is output, expected output, and predictions is what the model predicted. All right? Now, in an ideal world, these should be exactly the same, right? The model should exactly predict what I'm expecting, right? So, but as you know, like when you do this, so that's why we say this is my output, this is my predictions, calculate the mean square error, calculate the mean absolute error, right? Simple, just Y in predictions, and RMS root MSE just simply take the square root. That's it. And so when I do this, kind of prints it out, right? Mean square error, right? MAE, all this stuff. And one thing you will see, like mean square error always larger than MSE, because why? Because remember, it's squared. So when you square, what happens? It sort of amplifies the errors, right? And that's exactly the point, because that actually gives feedback to the algorithm. Say, hey, you're kind of deviating too much. Go back to the other value, right? So that's why mean square error is preferred most of the time, because when you make large errors, it's like it's giving very strong feedback. It's like almost sort of kicking you, right? It's kind of giving a strong kick. Say, no, you're gonna going too far off the track, right? So the algorithm will converge back up. Okay. Anyway. So that's pretty good, right? So this is the full algorithm. You can actually, right, complete data, right? Starting the data, kind of do like a little plot, calling the algorithm and all this. So the question was, can you choose the estimation when you plot the model? I believe you can. Doug was asking the question. Look at the documentation. When you initialize this, you should be able to specify the error metric. Actually, maybe not here. I think here. Right. So look at the documentation. I haven't looked at this in a while, so I'm a little rusty. But yeah, if you look at the either linear regression or fit method, you should be able to specify the error metric, right? And you know, if not straightforward, you know, there should be a way you can sort of say, okay, hey, fit this using MSE or MAE. Yeah, yeah, should be either here or here. I'm not sure which one. Yeah, so you can sort of look at the doc to see. Yeah. Very good. All right, guys. What else here? So let's see how you're doing. Okay, so we'll zip through the notebook real quick. Now, the previous data was synthetic data, right? We just asked, you know, psychedelic regression. And I always start you guys with this one. You will notice on all the labs, I'm kind of starting you guys with this one because the reason is this way it makes the data readily available. Then we can focus on the algorithm. Now, let's kind of, you know, look at some real world data. So let's do the billing and tipping example because even though it's kind of a, you know, kind of made up example, but still it's a good example. So here I'm saying create some billing and tipping data, right? So we are creating a data frame, just two things, right? Bill column, tip column. This is my input, right? This is my output, right? So this is what I'm trying to predict, all right? So we can, you know, so now we can sort of do some basic analysis, like say, okay, say, you know, describe the data. So you can see what's the minimum, what's the maximum, right? What's the average, all the good stuff comes up, right? And again, you know, I only have 10 data points, not a whole lot, right? Very small data, okay? Okay, plot the data, very good, right? So you can sort of say, yeah, seems like a, you know, linear regression here, okay, good. So let's do it here, right? So now I always recommend you guys extract X and Y. So this is something you will always see me kind of following, right? I always say, you know, you have some data point, right? Some data frame. That's your original data. Create X equal, you know, some formula, right? And also Y equal some formula. So create X and Y from your data. And you will see this actually, you know, you will spend quite a bit of time doing this in like real world data, you know, creating X and Y, okay? And that's part of it. And that's why I sort of like the, you know, the synthetic data because, you know, X and Y is, you know, kind of, you know, basically, you know, just one line of code, right here. But in real world data, we'll kind of do a lot of data shaping, a lot of data cleanup, you know, again, you know, everything you guys went through, right, so far. You will do all this. Finally, you'll get X and Y, okay? All right, so I got my X and Y. And here's pretty simple. My X is just, you know, bill column. My Y is simply tip column. That's it, right? Just single column input, single column output, right? And you can, you know, print out the data and all is good. All right, regression, very simple, right? So SQL, so, you know, so I like this one. So this is like, you know, you can sort of do this in one shot, right? So this is called chaining in scikit-learn. In scikit-learn, the way API is written, you can sort of do like chain, like you can say X, right? Fit, right? Transform. You guys have seen this, right? You can sort of do them in one line, okay, which is pretty cool. I mean, it makes code much easier to read. So here, what we are doing is we are creating a regression, and I'm fitting X and Y. Okay. Oh, sorry, I forgot to execute this here. Okay, X, Y. Okay, that's the regression's done. Doing the predictions. Right? Again, same thing, right? So here's a cool thing, right? So here I sort of ask, okay, hey, you know, I mean, if you just look at the numbers, it's kind of hard to make sense of those. So I said, okay, put the numbers side by side. Remember, this is my original data, right? Billing and tipping. Bill data, original data, tip data is what I expected. Let me kind of plot, you know, predictions side by side. You can sort of see the numbers, right? Actual is 12. I predicted 10.7, you know, right? So here I'm a little close, 13, 13, which is close, 8, 8, right? So you can see predictions are kind of getting close, right? But, you know, I mean, here I'm sort of visually inspecting the data, but, you know, usually what we want to do is like, you actually want to like calculate the coefficients, right? So my coefficients, again, the model coefficient will give you the data, right? The intercept is this, right? And here is my my scoring. Remember we talked about R squared and everything, right? So here my simply model says, what's my R squared? 0.90, meaning 90%, which is pretty good. Remember R squared, the maximum R squared can be, you know, 100, right? 1%, sorry, 1 or 100%. So here my R squared is pretty high, Because why? Because the data is pretty well behaved data, right? If you look at the data, right? I mean, it's a pretty well behaved data, right? So you probably won't get 100%, and close to 90% in a lot of the real world scenarios, but here we do get it, and that's good, right? And then you can calculate mean square and all this stuff, right? When you do the plot, again, original data versus prediction data, you can see it's kind of going through pretty well through here. Nice, right? So again, simple regression, right? And as you can see, right, all these functions are again part of scikit. We simply have to call this function. That's it, right? So we don't have to calculate and do the basic calculation. Now all of the functions are available. We simply have to use them and interpret the result. So for example, when I say r squared, I say, okay, r squared is 90%. That's pretty good, right? Because typically r squared between 0 and 1. I mean, there are some cases r squared can be negative, but we won't get into that. But let's assume r squared between 0 and 1. So as it's approaching 1, that is pretty good, right? Meaning the model can explain the data pretty well, right? That's very good, right? So good notebook, good here. And then also, so here, let's say, the whole point of it, we did this is like, remember, we got the equation right. Can you predict on new data? Okay, let's do that. So here's my new data. So I remember when I create new data, I don't have the tip amount. Remember, because right? It's like I'm only giving you the input and say, hey, here are the bill amounts. What do you predict the tip is going to be, right? So when you create new data, you probably you will not have the answer, right? That's what the model is going to do for you. Like for example, let's say you're a house builder. You are saying, hey, this is my new house specs, like this many bedrooms, this many bathrooms. What do you think this house will sell it for? Because if they know the answer, then they don't need the model, right? So the model is going to predict the answer here. So I'm saying, okay, hey, here are the bill amounts, 100, 200, 300. Can you tell me what the tips are going to be? So it says sure, right? It says, tip amount 100, bill amount 100, predicted model is predicting around $22 as a tip, right? 200, you guys get the idea, right? Now you can sort of see here, right? I mean, it's basically about 22% tip, right? So I mean that's reasonable, yeah. So is that gonna make sense, guys? Right? Any question on this one, billing and tipping?
Yes. So for the r squared value, do we want one that is closest to 1 as possible for correlation? How do we present that in, like, let's say a presentation?
Good question. Let me actually, yeah. So r squared is a pretty generic metric. Yeah, you want it to be as close to 1 as possible. Yeah. So so it's kind of like remember you're taking this course, right? Let's say you guys are doing the assignments and everything, but let's say somebody said, okay, how did you do? We're going to give you a score. We're going to say, okay, hey, this course you scored 87%, right? So it kind of culminates all the statistics and kind of reduce like one single number, which may or may not be fair, but at least it gives you like one number to talk about, right? So if you say, okay, how did you do in this course? You can say, I scored 87%, right? So that's how it is. So r squared can be like a one good number to kind of, if you just need like one number to talk about, this is a good metric. And trust me, there are a lot of other metrics. People will talk about things like p-value, t-value, and all the stuff, right? I mean, and they can get kind of more into stats. But there are a lot of other metrics. But to me, r squared is like a very good and simple metric to start with. Does that make sense?
Yeah,
So
thank you.
I would say start with this. And if you need to kind of, go more deep diving, definitely go more deep diving. Yeah. All right. So let's see. All right. All right, good. Yep. So again, I mean, yeah, as your model gets more complex, there are other metrics as well. Yeah. Let me see here. Housing data. Okay, that's good. All right. So let me go through the housing data real quick. So we have about 10 minutes left. So I'll zip through them real quickly. And I think this is a good, I think it's looking good so far. So, all right. So we are reading the data, right? So there's a house sales data. You can sort of see here, right? The typical house sale price. This is what we're trying to predict. And I'm asking you guys to kind of use any of these attributes to predict the sale price. Now you can see the data is much more complex, right? It's no longer simple billing and tipping data like we had before, right? Right? That was a nicely behaved data, right? Just simple billing and tipping data, right? That was nice. But now we are looking at real world data, which is house data. Okay, let me go through here. So I have lots of columns. Now the question for you guys is like, which column should I use, right, to predict the sale price? And that's kind of the question I asked you guys, right? So, and we'll work through this one. So again, so here's doing some basic cleanup, so drop all the null values. And basically, my shape is that we have about 27,000 records. That's pretty good, right? Describe column, right? Again, we sort of get an idea of the, right? And remember, this is the reason I choose the data is, you're already familiar with the data. You do know there are outliers in this data. Remember, when you look at the bedrooms, remember, we talked about this, they're like 0 bedroom and there's like a 33 bedroom, right? So, right? So, that, there are outliers here, right? But let's go with this. Let me see if I can simplify it. Okay, yeah, right? Yeah. All right. Now, what is my X value? My X value is no longer a single column. I'm asking you to consider starting with at least 4 columns, right? So I said, okay, you know what? Let's start with bedroom, bathrooms, and building grade to start with, right? To start with, okay? And that's what you guys are starting with. So I'm saying, you know what? Input column is basically bedrooms, bathrooms, the square feet of living, and the square feet lot. And what am I trying to calculate? I'm trying to predict the sale price. That's my Y. So my X is multiple, right? That's why X is, remember X is capital, right? Again, kind of convention, right? This is my X and Y, right? And if you look at, if you look at the X, print X, X dot shape, you will see. Right? So X is, 27,000 rows and 4 columns, right? We print the Y shape. Again, 27,000 rows, just one, right? Y is just one. Y is just one. At the end of the Y is what? Just one number, right? All right. So now I got my X and Y sorted out. Pretty good, right? So I got my X and Y. Now, one of the things I kind of ask you guys, start with these. If you look at these data, these are numbers, right? So, like if you look at the right, right? Actually, the actual data, these are numbers here, right? So I don't like, for example, I don't consider you to consider property type because then what you have to do, you have to actually do the conversion. Remember, we talked about this on the previous things. We have to convert this from categorical variable to numbers, either one-hot encoding or index assignment, something like this. So we don't want to do any of this just now. I simply want to just start with and just say use numbers. So these are right, bedroom, bathroom, just numbers, right? That's why we are starting with those. Okay. All right, X5, X5. Okay, now we are dealing with real world data. We have to split the data, right? Remember training and testing. We talked about why we do this, right? So X train, X test, Y train, Y test, right? Simple one-line code, and we are reserving about 20% for the testing, right? So basically, what's happening is 20% data for testing, right? And also the reason random number status is set to a number is we can repeat the experiment. So you guys, right? You guys remember if we don't set the random number, every time I do the division, I get different X and different Y. And that's fine, but if you're experimenting, that's not good because then your train data keeps changing. So that's why we fix this by using a random number, right? So a lot of the time when you look at the code, use a random number set to just some number, whatever the number is, some integer number, right? And we talked about 42 and all this in the last time, remember? Yeah, okay. So X train, Y train, all right. So let's look at the shape of X train. So print X train shape. And then X test also. Okay, so let's see how my testing and train split went, right? So testing, okay. Capital X. All right, cool. Remember I had 27,000 records, right? Out of 27,000, I'm doing a 80-20 split, 80% for training, 20% for testing. So my training data has 21,000, testing data has 5,000. Pretty good, right? Again, just one line of code. Okay. Same thing, linear regression, all right, fit. Now, when I do the fit, we only train on training data, meaning do not do this, right? Don't say, fit X and Y. Why? Because remember, we actually want the model because, if I give the entire data, then basically I have no data left to test the model because the model has seen all the data. So that's why when you train the data, we are giving X train and Y train. Very important, right? So, and now you guys know, why that is, and we talked about all this, all this in the last class, right? That's it, done. Print out the coefficients, right? So you can sort of see here, when I print the coefficients, I'm getting 4 coefficients, right? Because remember, my inputs are 4 inputs. So each input is getting a coefficient. Does that make sense, guys? Right? So bedrooms, this, bathroom, this, cover living, all this, right? So one thing I look for here is I like to see if there are any coefficients that are 0. So do you guys see anything that is kind of 0? Not here, right? But square field lot seems to be very close to 0. Let's say this is 0, just for argument's sake, let's say this is 0. What does it mean? Like, what does it mean, like, when this coefficient is 0, what does it mean?
Irrelevance.
Exactly. The model basically says, okay, you know what? This field doesn't matter. Because, whatever the field value is, right? When you multiply this by 0, again, this is not 0, I'm just making an example, right? Let's assume this is 0. If you multiply anything by 0, what do you get? 0. So sometimes you will see some coefficients are becoming 0. And so it's always good to keep an eye out to kind of see, okay, which coefficients are important and which one of us, zeroing out, right? And some of the model will tell you. So if they, so here it's kind of, right? Nothing is 0. That's good. If you have 0 coefficient, then that means like, something you got to go back and to see what if there's something of the data or not, right? Because at the point it's saying this column doesn't matter, so I'm zeroing it out, right? So, all right, guys, good. So, right, again, like I said, it doesn't matter how complex the house sales data is, right? Once you get X, right, X and Y figured out, split the data into training and testing, just one line of code, right? And that's a beauty of these scikit-learn. So easy to use API. All right, let me finish this up. Okay, we did the training. We printed the coefficient. Again, we are wondering why I have multiple coefficients, because I had multiple inputs, right? Let's say, for example, I had 5 inputs, like X, A, B, C, D, E. You will see 5 coefficients, and you can sort of map the coefficient, right? And so here's kind of right. You can sort of see square field load, is multiplied by this. So kind of the equations kind of like, if you really want to kind of look at the equations, it'll be something like this, just to kind of give you a sense. Again, not exactly accurate, but kind of like this, right? You can say sale price equal, right? Square feet lot multiplied by this guy, right? And then bedrooms multiplied by this guy. You get the idea, right? And so on and so on and so forth. That's my equation. Pretty good, right? So again, it's a linear model. Why? If you look at the data, it's linear, right? But we have multiple attributes. So if you're trying to sort of visualize this graph, imagine I have 4 variables. So you got to kind of visualize the graph in 5 dimensions. I cannot, right? So, but you can get the idea, right? But like I said, like math, doesn't care how many dimensions we have, right? So you can add as many dimensions as you want, right? The equation is still linear, but just more variables. Okay. All right. So let's predict on the predicting. So we are predicting on the test value. Remember, when you do predictions, we train on the training value, right? And then say, let me say print y print, right? Just a bunch of numbers, and these are sale prices, right? So let's see if we can. Okay, so let me do this here. Okay, so let me do this here. So again, all the metrics. Let me do one more thing here. DF. Okay. Let me do this. Let me show you guys one more thing real quick. DF. Okay. think I think we should do it. Okay. And I always get this wrong. Okay. Okay. And then, all right. So what I'm trying to do is like this, right? Predicted price is YPRED. That's going to come in. Okay. Yeah. So. All right. Let's see if I can do this. All right. I was trying to put the predicted price as YPRED. Let's test. Do this one more time. Oh, sorry. It's now. Okay. Sorry. Yeah, that's why. Damn it. All right, guys. One more try, and I will stop this. Running out of time. Check columns. All right. I will. Okay. So what I was trying to do is like I was trying to sort of display this side by side, but I'm not getting the syntax right. I'll skip this for now. Right. So let's look at the metrics. So R squared. Interesting. I'm only getting 44% as my R squared. Remember? So it's, last one we got 90%. So here, right, we are not doing that well. Why is that, guys? Right? Can somebody tell me why my R squared is not doing so well here?
Is it because of the variable whose coefficient was 0, or no?
Yeah, that could be possibly a reason. Exactly. Yeah. And so this is a point of when we look at these things and say okay, what do we learn, right? So we started with very simple attributes. Remember, our attributes are basically right these guys. So my algorithm only considered these attributes to calculate the sale price. So these are important attributes, but there are a lot of other things we're ignoring, right? For example, we are ignoring property type. Where's property type? Sorry, up here, right? We're ignoring property type, right? And if you look at this, there could be some, a lot of other things we could include. For example, you can say, year built. Maybe that might make a difference, right? Maybe algorithm should consider that, right? Or things like, traffic noise, or, somebody mentioned zip code, right? We completely ignoring zip code because zip code plays a huge value. So now what you're doing is you're playing feature selection. Remember this, right? This is what we did a couple of weeks ago. So this, let's say, this data has what, I don't know, let's say 10 or 20 columns, right? Out of the columns, 20 columns, which ones are important, right? So a lot of the time, there are some algorithm you can sort of use to kind of figure out which are important features, but a lot of the time you're going to depend on your domain expertise to say which features are important to my model, right? So that's why I sort of had you guys started with like a very simple, like, these 4 attributes, okay? And has anybody kind of played around with the features and, has anybody used, any features that, increase the R squared?
Yeah.
Yeah. What features did you guys try?
Well, I made the loop actually to go through the log.
You did like
calculating the coefficient, with all the things, and I found out the field that's actually the major one, by far away from all others. But anyway, I'll let you continue.
Yep. So for example, let's say I'm going to add like a new feature. Let's say, for example, I'm going to add, I don't know, like square feet in basement, right? Just to kind of, right? So you say, okay, let's add a square feet in basement, and let's see if that that makes a difference. Okay, so let me run this. So simply run on, and this is why I allow it in Jupyter Notebook, because you can just run the whole thing, right? Okay, let me go here. Okay, I'm bringing the R squared. Okay.
The other thing to add on the previous question we had, if there is a trouble with adding features with
Right.
coefficients,
Ah,
doesn't matter. It only does matter if you add a lot of features that they don't have good coefficients. It's just you're increasing the computation time.
right. Okay,
Not
so
the
1 second.
result.
Yeah, let me give me one moment. Yeah. So because it's kind of waiting for me to answer the question. Okay, one second. Sorry. Yeah, please go on. Yes. So in this case, we are doing a sort of kind of a very quick trial and error method, right? Let me see. I want to make sure we are good to go here. Oh, okay. Sorry. Yeah, I'm going to turn this guys off because otherwise it'll kind of keep waiting for me for your answer. Okay. I'm just taking a shortcut here. Okay, very good. All right, so I'll skip this. Okay, ignore this guy. Doesn't matter. Okay. All right, good. So let me ask you, right? It's been from, just, it's not really improving much, right? What else? So I'm kind of curious. Has anybody tried any other attributes to make this R squared, go better? You remember, we want to get to as close to 1 as possible, right? And that's part of the fun of this whole thing, right? So out of all this, has anybody tried anything?
I did a similar analysis for housing prices with a different data set, and I found grade to be one of the highest correlations with price.
Oh, building rate. Okay. Yep. Let's try that. So square feet basement didn't really produce much results, so I'm going to do building rate, right? So again, so run all. Okay. And so this is the point, you want to actually, get some, get a little use of domain knowledge. So let's say we need the building rate. Let me see, where's my R squared? Oh, cool. R squared R squared went up by, remember we were at 44%, right? So kind of, keeping log of this, right? Kind of, if you just really want to solve, right? Variable or feature selection. So initially I started with, right? I'll wrap this up quick. So initially we started with bedrooms, bathrooms, square feet, living, square feet lot. So we're around 40, around 44%, right? Basically, I think, right? Then we added, what did we just add? Building rate, right? So now I'm like 47%, right? Or let's say 48%, right? Yeah.
Someone in the chat got an R squared value of 83%.
Oh yeah. So let's see. Let me see. Let me see land value. Oh yeah. So you're adding land value. Very good. Okay. Yep. So good. Okay. So they added land value. So let's try that. Okay. Good. So let's go and add. Is there a building rate involved as well? No. Okay. So just set land value. I know this will do really well because I'll explain why that is. So I'm at a land value. Let's see the numbers. Kind of slow. Okay. All right, coming up. Oh, look at this. When I added land value, what happened? See, I jumped from 85%. That's pretty good, right? So adding land value, I gone from 44% to 75%. That's very good, guys. So I went from 44. So that's a 30% increase, right? That's pretty good. Now, can you explain, somebody explain this to me, why this matters? Yep. So,
what do you mean by why it matters?
So remember, with bedroom, bathroom, square feet living, I was at 44%. And when I added land value, my R squared went to like 75%. So why did land value make a big difference, guys? So that's what I'm gonna, right? That's what I'm gonna ask you to kind of justify this.
Probably has a good correlation of some like 1 or -1 to the data. So like, what has been linear regression probably has correlation of 1 to the data.
Yep.
Right.
Yep.
So it's gradient.
Exactly. And also, this is a bit of a, I mean, this is why you need to kind of understand housing market. Your house price, right, is basically price of land plus, price of your building, right? Okay, so buildings are called improvements, right? So which one do you guys think is most expensive? Is the land more expensive or the building more expensive?
Land.
Land, right?
So according to these results, land, right?
That's right. Of course, it depends on where you live. But in big metro areas, land is a premium, right? So a lot of the time, you might see people just, let's say, people just an old house on the, in the land, they will just buy the land, demolish the old house because that's just too old, and they'll build a new building, right? New house, whatever, right? Because why? This is the most usually, right? Again, there are exceptions, most expensive, right? So land is the most expensive part of the house price. So your land value directly reflects your house prices, right? And that's why when you guys said, and somebody said, was it Alan? Yeah, when Alan said, when you're adding land value and so basically building is basically called imps, improvements, right? I think imps value, right? When you add these two guys, that directly correlate your house price. And you can find this out, right? You can sort of go and say, you can do like a little correlation matrix to see which one actually highly correlates. You can say df correlation, right? And kind of see, right? It's kind of two, right? For example, if you look at this, it's just too many metrics, but you can see the land value. Sorry, look at sale price and land value. Kind of hard to, let me make it a little smaller. All right, hopefully you can see this. So this is my sale price, right? So second row is the sale price, right? See which one's highly, sale price and sale price, of course, correlation 1, right? Because they are the same attributes, right? And you can see square feet living, 68%, very important, right? Land value, you will see somewhere here, right? 79%. Improvement value, 80%. Remember, these are like, percentage, right? Bedrooms, only 31%. The square feet lot, only 15%. See what I'm saying, right? So looking at correlation real quick, you can see why adding land value. Zip code, right? No, honestly, zip code, it's not really, at least in this data, zip code is not correlating very well, right? But remember, zip code is special, right? Zip code is not a number. It's actually like a categorical variable, right? So ignore this for now. But if you're just looking at numbers, you can see land value, improvement value, they are huge factors in determining your house value. Like for example, traffic noise, almost 0, right? Meaning that doesn't matter, right? Year renovated, almost equal to 0. Year built, also almost equal to 0, right? So, and this is what's important, because you might think year built might have a big impact. As it turns out, it doesn't. And how do you figure this out? Simply by doing a one-line correlation matrix. Now you guys know how to read the correlation matrix. Remember, now that's what we went through in the first few, like in the diagonals should be all 1, right? It's between -1 and +1. So we are looking for highly correlated. By the way, you'll see there's another one, 98%, right? So this is cheating, right? Basically, this is like adjust the sale prices. I think they adjust based on some local tax code or something, right? So don't use this, right? This is like this is after the fact, right? So that's why it's 98%, because that means it's basically calculated from the sale price. So I know in the last class somebody said, oh, I just the sale price and I got like pretty R squared, almost close to 1. So that's, in real world, you will not have this. right? So again, so parsing the data kind of requires a little bit of a domain knowledge, right? You need to understand how the housing market works, right? For example, you should know, yeah, just sale price, this is not something you will get in new data, right? Because this is only after the fact, right? Meaning only after the house is sold, they will adjust the sale price, right? For like inflation and loan interest rate and all that, right? So that's after the sale price is determined. But our goal is to determine the sale price, right? Meaning using everything else, and that's why. And let's do one more thing. Let me add IMSVAL. I just like you guys did IMSVAL. Let me run through real quick, and then we'll wrap it up. All right. Good, guys. Okay, so we're at IMSS value. Let's look at R squared. Oh, look at that. Went to 82%, right? So this is the fun part of machine learning, right? When you add, IMSS val, now you went 82%. I mean, that's not bad at all, guys, right? Think about it. Like just using a simple linear regression, right? We were able to, predict with the 82% accuracy. That's not bad, because housing prices are very, how do you say, it's a very complicated data set, right? But here just using a simple linear regression, we can do we can do pretty well, right? Not like something like Zillow, but still 82% is nothing to sneeze at, right? So anyway, so you can still see here, right? I mean, even a simple linear regression can help you quite a bit if you understand the data really well. Good, guys. Let me stop here. Any questions? I know we are slightly over, but I just want to get get these guys done. So again, thank you, Ahmad, for a really good notebook. So again, so when you guys submit this, I randomly pick a notebook, and and when I see a good solution, that really makes me happy, right? It's like, yeah, so because this is something you guys did, and you guys went through it on your own, right? And I you see, I'm sort of adding some things here and there, but mostly augmenting, right? So 90% of the code is still yours. So good, guys, very good. So what did we do? Quick summary, right? We basically looked at linear regression, right? Look at our right? So you understand, we started with linear regression. Again, even though it's a very simple regression, there are a lot of concepts. So things like training and testing, right? Error metrics, what are we optimizing for, right? All these, we are understanding, okay? Next week, we are going to go to the, all right, so as algorithm map, we are going to go to logistic regression, right? That's next week. And as a matter of fact, it's actually a classification algorithm, right? So kind of, right, like a little different. So your task for next week, I'm asking you to read a little bit about classifications and also start with logistic regression. Okay? And I checked in all this stuff, so take a look at this. Your reading list is already there, and also the exercises, right? So kind of work through this. So now things will go pretty quickly, guys, because we kind of have the fundamentals under our belt now, right? We understand things like what's the error, what's what is MSE, right? All this stuff we can talk very confidently, right? So we're kind of building up on this, and you will see the algorithms themselves, right? And that's what I always tell people, like once you understand the basic machine learning, right? What's the algorithm? Just 2 lines of code, right? And that's why scikit is such an easy language, easy package to learn, because it doesn't matter what you can say, even a complicated algorithm like random forest or XGBoost algorithm, just 2 lines of code. Most of your work is going to be basically, figuring out X and Y's, X train, and right, all this kind of stuff. So that's a human loop, right? The algorithm, once you figure out your X train and Y train, it's like just 2 lines of code to get this going. That's it. Okay, so keep this in mind, right? Focus on, right? So the takeaway is basically not just using the algorithm, because that's the easy part. Understanding data, choosing the right algorithm, right? And as we go forward, right? For example, in classification, we're going to look at multiple classification algorithm, right? So one week, I'm going to give you guys a problem. You're going to evaluate like 3 or 4 different classification algorithms and pick the best algorithm possible, right? Because that's how you will do in real world. Okay, so we're kind of working your way towards that. Does that kind of make sense, guys? Good. All right, guys, that's it. Sorry, slightly over, but thank you. Thank you for sticking with me. So please look at your, look at your guide. I will upload them. So next week, basically, we are moving into classification and logistic. Okay, so good, guys. Thank you so much. I'll let you guys go. We'll talk next week. Yeah. All right. Excellent. Thank you, guys.